Now, I wanted to record a video to talk about the loop of Henle, or nephron loop. So remember, when we're looking at the nephron, we've got the Bowman's capsule, the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, and the collecting duct. And this loop of Henle and collecting duct are going to be in a part of the kidney that's called the medulla. And the medulla is salty as you get deeper in it. So this part of the medulla will be super salty, and as we get shallower in it, it'll be less and less salty. And this actually creates this really interesting effect. What happens is, as the loop of Henle travels through the medulla, the fluid inside of it is going to try to equilibrate with the environment surrounding it. So as it's going down, in attempt to equilibrate, the only molecule that can leave in what we call the descending limb is water. So water is going to start leaving, and in doing so, it's going to create a more concentrated urine. Now, once that fluid rounds the medulla, at this point, it's very concentrated. As it starts to go to less salty environments, now something needs to leave. So again, the fluid in the loop can equilibrate. This ascending limb is only permeable to salt. So here, the salt goes out. And in leaving, now we get to a point where the filtrate is back to sort of a normal salinity. So to sort of recap, it starts normal, it gets salty, saltier, very concentrated, and then it's going to have to get less salty. So it's going to lose some of that salt so that it can equilibrate with the environment around it. But then we've got this problem, and the problem is what happens to these molecules of water and salt that are hanging out outside of this loop, and why aren't they messing up the concentration gradient? And that's where you've got a vessel that runs around this that's called the vasa recta comes into play. The vasa recta goes in the opposite direction of the loop of Henle, and as the blood is flowing down into this saltier area, the blood now wants to equilibrate with the surrounding area. It's going into a saltier area, that means it wants to become more salty. So it sucks up this salt that was left off by the loop of Henle. Then, once it makes it around the bend and it starts going through less salty scenarios, it's going to start taking up water to, again, try to equilibrate with its surrounding environment. So I always think of the vasa recta like a vacuum cleaner that's coming through and sucking up all of the stuff that's left behind by that loop of Henle. Now, the longer the loop, the more salty the solution around it gets. And what that means is that a longer loop of Henle, so if I draw in one here that goes all the way down here, this blue loop would have a greater concentrating power than the black loop that I drew. And that's because it goes through a greater difference in salinities, and that's going to drive more of the water out, and as a result, concentrate the urine more. The thing that I always found really frustrating about the loop of Henle when I was first learning about it was that it didn't make sense to me that you take out water and you take out salt, and at the end you end up with the same concentration. But the real key is in what is left when we reach this point. And it turns out that what you've done is you've taken out sodium, which is very useful. You've taken out water, which is very useful. And what's left in here is urea, which is a waste, and other waste ions. So what you've basically done is you've kind of gone through this massive 5-gallon drum of garbage, and you've picked out all the recyclables that are useful, and you picked out all the compost, and now the only stuff that is left in this tube is the bona fide waste, and it is at this point pretty much destined for the toilet, with the exception of a little bit of fine tuning that's going to happen at the distal convoluted tubule and in the collecting duct. So in a normal scenario, as the urine is traveling through the loop of Henle, what's going to happen is that it's going to go from a condition where it's isoosmotic to the blood to where it has fewer solutes than the area around it. And what this is going to cause is water to exit. As that water exits, it makes the concentration inside the tube get greater. Now, as that fluid goes up, it's going to try to equilibrate with the surrounding environment, and that means that salt is going to get pulled out. So that's what should happen in a normal person. Now if we think about a diabetic, something really interesting happens. Diabetics have additional particles because they have excess glucose, which has entered their nephron and cannot all be absorbed by the kidney. In this case, what happens is we've got so much of a high osmolarity inside of that tube that it's not going to draw the water out anymore. And it's not going to draw the salt out anymore. It's basically going to keep the fluid within this tube. And by keeping the fluid within this tube, that means that that fluid is sort of destined for the toilet. So basically, because there's so much glucose in the tube, now we're not getting the benefits of that concentration difference through the medulla. And since we're not getting that, we're actually losing more water than we would. And that's why diabetics pee a lot.